Welcome back, folks. This is Dr. Alianna J. Maren, and I'm inviting you back into Part 3B of our study of the neural network's backpropagation method, specifically in this vid emphasizing the chain rule. And here, we're especially going to focus on how we use the chain rule to figure out the dependence of the sum-squared error on a given connection weight. We left off in our last vid for getting our general understanding of the chain rule. Now we're going to make it more specific and applied. Now, in showing you this equation, which I've presented in each of the previous vids, it's important to know that we haven't yet actually derived this equation. We haven't specified how the dependence of the SSE on a hidden to output connection weight actually shows up as each of these little parts. That's going to be in video 5, and the corollary process for the dependence of the SSE on an input to hidden connection weight will be in vid 6. Right now, what we want to do is just get the mathematics that we'll need once we get this equation so that we can effectively compute the simplified form or end result. So let's summarize our next steps. We're going to compute, ultimately, the derivative of the sum-squared error with respect to various connection weights. We're going to need this derivative broken down into each of its component parts. The first of those is the derivative, the partial derivative actually, of the sum-squared error with respect to the error term. Then we need the derivative of the error term with respect to the transfer function. That's f. Then we need the derivative of the transfer function with respect to the inputs into that transfer function. And finally, we need the derivative of the inputs into that transfer function with respect to a given specific connection weight that is leading into that function. And all of these derivatives, by the way, are partial derivatives. The key crucial step here is that our transfer function is now in itself a differentiable function. For simplicity, we're going to use the sigmoid, which is 1 over 1 plus the exponent of a coefficient, we're calling it alpha, times x. X in our case will actually be the inputs into a node. So the transfer function is really a composed function. It's got 3 distinct component parts. And to get the derivative of the transfer function with respect to a specific connection weight, we need to have this transfer function broken down into 3 specific derivatives, each of them multiplying each other, and that's the chain rule. When we take a look at this transfer function, once again, we're going to see that it's in those 3 parts. The first part is 1 over a function, and that function that it is over is the 1 plus e to something. So that's one derivative. The next is the 1 plus e to something. That's the second function, and we need the derivative of that. And the third is that something, we're calling it h, which is the negative of a coefficient times x, where x is the inputs into that transfer function. We're not going to worry about that now. So breaking it down. In the first case, the derivative of 1 over something is the same as taking the derivative of that thing to a minus 1 power. So we use our power rule from basic calculus, and that gives us minus, because we've got a minus 1, times that thing, in our case our thing is g, to the minus 2. In our next step, we take a look at that function that was actually in the denominator earlier, and it's 1 plus e to something. We're calling that something h. So the derivative of 1 plus e to the h is simply e to the h, because the scalar term of 1 drops out, and the derivative of e to the h with respect to h is e to the h. The derivative of the exponential function has that wonderfully unique characteristic as being the same as itself. Our last step is that we're going to go inside that h. H is minus a times x, a also being sometimes alpha here, so the derivative is simply minus a. So we're going to put all these together. We're going to substitute the various terms into this formalism that we've just worked through. Then the final step will be the derivative of the inputs with respect to a specific connection weight. That's going to be the derivative of a sum with respect to a specific term. This is our last big step in figuring out the various components from the chain rule that we need in order to determine the dependence of the SSE on a specific connection weight. So we're going to write down the partial derivative of the set of inputs into a given node, that's node input sub k, with respect to a single specific connection weight going from hidden node H to output node K. Now as we write this down, we see that the inputs are a weighted sum. That means that we're going to take the sum where the running index takes us from 0 up through H minus 1, where H is the total number of nodes in the hidden layer. The sum is the connection weight that leads from a specific given hidden node up to a very specific output node, that would be output node K, times the strength or activation coming out of hidden node H. Now because it's a sum, we're going to write this down just for fun as a set of numbers that are added together. We're just doing this to get a look at things. And we see that if we want the dependence of this node input on one specific connection weight, then only one of those terms is applicable. The rest of them don't involve that particular connection weight, so we can drop them all out. Once we do that, we're left with a very simple derivative. We're taking the derivative of v sub hk times h sub a with respect to v sub hk. And in this case, we have a very specific hk in mind. So it's very simple. The activation of node H, which we're representing as h sub h, is the multiplier. It's the scalar constant multiplying the connection weight. So we take that derivative, and the surviving value is h sub h. It's the hidden node activation, capital H, at a specific node, small h. We do not yet have the specific equation for giving us the partial derivative of the sum squared error with any connection weight, but we do know, once we've got those equations in hand, how to compute those individual components using the chain rule. That means that when we do finally assemble that equation, we'll be able to plug in the various elements very easily. Now in closing, just for fun, let's give ourselves a little bit of homework. Let's take a look at that basic equation, and yes, we have not yet derived this whole thing, but we do know that we can write out an equation for the summed squared error itself. It's the sum of squared error terms, so that's pretty straightforward. And we want to take the derivative of that, the partial derivative, with respect to a specific error term. So one homework step that we could assign ourselves is to use the same kind of logic that we had when we took the partial of the inputs into a node with respect to a connection weight. Let's use that same logic and get the partial derivative of the sum squared error with respect to a specific error term. The other thing that we can do, since we already know the partial of the transfer function with respect to the inputs, we can do some substitutions there, and we can carry out the multiplications and simplify the results, and then we can compare results with what I'll show in the next video on the transfer function. So that's something to do between now and then. Thanks for your participation in what might have been a little bit of an arduous exercise if you haven't been doing chain rule differential calculus on a regular basis for the past several years. But we're done. All those little pieces are there. They're ready to be assembled. So this has been part 3. In our next video, we're going to do the transfer function. Not only are we going to look at the mathematics of the transfer function that we'll use, but we also will take a look at what the nature of this whole backpropagation process implies for the chain rule, and hence for the transfer function, but also what that means in terms of what transfer functions are now allowable, which ones will work for backprop, which ones won't, and that cues us up for one more very important step a little bit down the road after this series. But what we want to do is start our contrast and compare backpropagation Boltzmann machine, and it starts with the inside of the neuron itself. In backpropagation, we'll see that we need a certain kind of differentiable transfer function. In the Boltzmann machine, something very different, and we'll begin to understand why it is that these differences exist and they're allowed. Next one, transfer function. After that, 2 vids on the 2 different stages of backpropagation, derivations, where we actually put all these little pieces into place. By then it's going to go pretty easy. And then we do sort of an intuition or get a whole story, whole picture wrap up of the whole thing. So thank you for joining me. We'll see you in the next vid.